All right, let's continue the period, God willing, with the discussion we mentioned about the journey of nuclear imaging. We had started to touch a bit on the topic of accusation modes, and we talked about dynamic scan, static scan, and gated imaging, as well as the difference between SPECT and planar imaging. We talked about static imaging and the difference between SPECT and planar imaging. In the imaging process, so we talked about the differences that exist between the various types, whether it is planar imaging or others. We talked about in detail dynamic imaging and SPECT imaging, and we started discussing the topic of, in great detail, autocontour and the circular movement of the head in relation to the patient in the modes. The head was moving in a circular manner, in a very precise manner, or using autocontouring to get as close as possible to the surface of the patient during the imaging process. We also discussed extensively the topic of the phantom and mentioned that it is used in image quality assessments or tests related to SPECT or the gamma camera. We talked a bit about in-depth noise and its relationship with the matrix from the last time, as we mentioned previously, and that was also part of the discussion. And this was indeed. We talked about the topic of filters, specifically the high-pass filter, low-pass filter, and band-pass filter, their functions and their effects on image quality, noise, and background, as well as how the image appears. We also discussed the different acquisition modes like frame mode and list mode. Let's continue, God willing, with our discussion. We are also discussing dynamic imaging and how the region of interest, its shape, and usage allow you to calculate counts by time, giving you the time activity curve that you can create through the calculations or the spread function of the whole. So, just to let you know. The gamma camera itself, which is designed for this purpose, is a single head model. Single head means it has only one head, and this head is used for anterior, posterior, lateral imaging, and everything else. Of course, it can also be used if you want to perform a SPECT around the patient. Some companies today offer you a dual head instead of a single head. In the past, there was also a triple head, meaning there would be 3 heads in a dual setup like this. However, the triple head is not commonly used anymore. The idea behind the dual head is that it saves time during imaging. When you take images like a whole body scan, you need to capture both anterior and posterior views, so you start moving the anterior camera to take images, while at the same time, the posterior camera is capturing images. This way, you save time for the patient instead of having them sit for the anterior view and then moving to take the posterior view. The camera is available now, but of course most people think about the idea of saving money, meaning companies come to tell you, for example, that they will give you a dual head, but the price will be very high. So the price for the dual head decreases, especially since the difference is mainly in the acquisition process or time saving. Because of course, if you want to take, for example, anterior posterior views or oblique views for the patient, such as right posterior oblique and left posterior oblique together, or right anterior oblique and left anterior oblique together, then in this case, you can use the dual head to image the patient. This is the idea of the dual head. Of course, the dual head can be set in H mode in this way, or it can be set in L mode. The L mode is the configuration where the 2 detectors come closer together to form a 90-degree angle, which I call the L configuration. The L mode is considered suitable for cardiac cases, while the H mode, for example, can be used in cases of bone scan. we want to organize our thoughts and say that today we will talk about image quality and we will delve into quality assurance. God willing, we will try to cover the entire nuclear section. After that, I will move on to the bone scan and the artifacts present. God willing, we will try to address the topic of image quality. You have three main factors that affect image quality: contrast, noise, and spatial resolution. We may have discussed them last time and started talking about the details, but let's try to understand what contrast means. Contrast means you see something that has a difference. Let's talk in terms of CT or X-ray. Language: when something has high contrast, you see it very brightly against the background, or it has a distinct color. The text discusses the difference in background. Attenuation, for example, in X-ray imaging between bone and soft tissue. Bone appears remarkably different, or if you have a kidney stone, it shows up distinctly because it has high attenuation properties, making it appear bright against the background. The presence of contrast is very important in any imaging modality. Here, the topic is related to the contrast within the patient and the contrast in the image itself. The contrast within the patient is linked to the concentration of activity present in the object I am imaging. For example, if you have, say, a kidney that you want to image, the concentration activity of the kidney is compared to the background activity surrounding it. This is the ratio or difference between the activity of the object you are interested in imaging, which is the concentration activity, and the background, which also has a concentration activity lower than that of the kidney. If both are similar, there won't be a significant difference, and in this case, your contrast will be low. However, if there is a large difference between the concentration activity within the organ of interest and the background, then your contrast will be high. When I work on or express the topic of contrast for the patient, I refer to it as subject contrast. However, in my image, I do not measure concentration activity. I measure the counts present per pixel. I measure the counts that exist in the pixel. I take the region of interest in the area where I want to measure the contrast, for example, and I take this area and say, I want to know the counts per pixel here. Then I take the same region of interest, for example, in another place and use the same equation. Basically, here you are getting counts per pixel or per unit of area in a specific space or unit, calculating the counts present in your region of interest or the area where you want to take images, and then you look at the histogram. So the difference between the counts in the region minus the counts for the same area in the background gives you the background counts. From this equation, I can calculate the contrast. Here, for example, if you have a lesion present like this white area, this lesion is located inside the liver. If you take a line profile, what does the line profile mean? Previously, we said that you want to see the change in counts that exists per pixel, the change that exists per pixel, or per distance, for example, or over a certain distance along your line. So in the first area before the lesion, there was one liver with a high uptake, so the counts here are high. Then the count drops inside this lesion as if it is hypo, meaning it is not taking counts or not taking radiopharmaceuticals, and then it rises again because you have entered the liver area. So now you are taking a count profile or a line profile on this lesion. This first area represents the region here, and the second area is after the lesion, ahead. These counts are based on the concentration of the object in the water. What about the minimum for you? That is the area where your concentration activity is, which is where it is in the lesion itself. This lesion may have this activity if you are talking about the patient. The situation would be like this. But if you are talking about the image itself, of course, the matter will not be the same as the real contrast. I mean, the real contrast that should be seen is that the lesion is brighter than the background. The imaging modality itself does not have the efficiency to see the real contrast as it exists within the patient. It does not have the capability to see the real contrast that is present in the patient on the imaging modality. Therefore, there is a difference between the lesion count and the background, which is less than it is in reality. You will find this curve representing, for example, your value before the lesion, and this is the value after the lesion, and this is the value of the lesion itself. It adds to the pixel that I forget in the noise that you have noise in the image. So you find that the image shows up like this when you take a count profile because there is definitely noise present in the image. This is what I want to tell you about the difference between subject contrast and real contrast or image contrast for you, and what the relationship is between this count profile and that count profile. The whole idea is that you get the difference between the counts in the lesion minus the background counts, and you divide it by the background counts. This ratio is the contrast equation. If you want to express it as a percent, you multiply this value by 100 to get the exact percentage of the contrast present in the lesion. Now, what does the contrast or the amount of variation depend on? What factors can decrease or increase the contrast? From this equation, I have SL, which is the count per area in the lesion, and ST, which is the count per unit area in my background or the surrounding tissues. When do you think the contrast increases, and when does it decrease? When do I see the lesion very clearly, or the organ I want to see very clearly, and when do I not see it clearly? Logically, if the difference in counts between the lesion or the organ and the background is small, then it won't appear clearly. This is natural and logical. Well, can this happen? Yes, it can happen if the radiopharmaceutical labeling you performed is not with a labeling efficiency of more than 90%, meaning it is not sufficient for the organ uptake significantly. There is a high percentage of free technetium present, and the free technetium increases the background present, which consequently reduces the contrast. So does the preparation of the radioactive material affect it? Yes, of course it does. Also, the administrative activity, the activity itself that you are labeling, if it is a low dose or less than the standard activity we are working with, the same idea applies. You will not get enough counts, and thus the image will also have reduced contrast. Additionally, scattered radiation may be present. This scattered radiation could be from the patient, and it can be high, especially with a patient who may be fatty, or if the patient is moving. All of this affects your contrast significantly, so even using a different collimator can drastically change things. For example, if you use a different collimator, your counts may increase or decrease substantially, which will affect the counts you obtained in a noticeable way. All of this has a considerable impact on you and your work. Also, one of the important things to note is that this image you have clearly shows you the difference in contrast with changes in the energy window if we remember our curve and how it behaves under different conditions. I had the curve like this, and I was taking a window in a specific area and saying, well, this window is 20%. I want to take the counts in this area. Now, if you come and enlarge the window from 20% to 40%, you have included some of the Compton part with you, and this part is scatter. So, what should it do to the image? It will reduce the contrast of the image, meaning it adds true activity distribution. The first image is fine. Here, for example, this is a 20% energy window, and this is a 50%. You will find that the initial image is better than this one. The more you widen the window, the more scatter you have in the image. The more you want to differentiate between the myocardium, the white circular part, and those two circular rings. You have a round part here. This is the myocardium. This phantom I created looks like the heart muscle. The first round part is the myocardium, and the second part This ring resembles the left ventricle, and here is the right ventricle. This is like the same image of the heart that we see when we take a cross-section of the heart. But the idea is that by increasing the window, I will place a material in the phantom and start to see the same activity that is present. The activity remains the same. All that was done was to increase the window and observe the effect on image quality. Therefore, increasing the window or energy window will reduce the contrast present in the image. Now, what is the curve drawn below? The curve drawn below shows the amount of contrast in the line profile that you will create. For example, in the first image, if you take a line profile like this one, you will find the curve that represents the true activity distribution, which is sharper. The curve you see going up and down can be considered as if it is creating a sine wave or a wave pattern, where the peak is very high and the bottom is very low. Why? Because there is a difference between the high activity present in the myocardium and the low activity found in the background, so the curve reflects that difference. Let's take, for example, unscattered photons. Here, it only considers the 140 without including the window or the scattered photons. You will find that the curve represented by this second color resembles a sine wave. If you take a line profile here at the background area, you will find counts. Due to scatter, it wants to drop to the bottom, to your value, but it doesn't know why, because there is a count here in the background. It starts from this area, rising within the myocardium, and then it begins to drop again. However, the drop in the cavity will not be the same as the drop in the true activity distribution, because you have scatter photons. In the 20%, you will find the same situation. Here is the 20%, and here is the 50%. Thus, the increase in the window has increased the scatter photons, and the scatter photons have reduced the contrast of the image. Noise. In this story, we can talk about the same concept and meaning as I mentioned earlier in the lectures. If you enter a place where there is a group of people and all the people there are 150 centimeters tall, is there any variation among the heights? There is no variation. All the people are 150 centimeters tall. Now, if you enter another place and find that the heights of the people range from 150 to 200 centimeters, in this case, there is variation among the heights of the people. The amount of variation is what is expressed as noise. What is noise? It is the standard deviation of the square root of the mean value. What is it? Exactly. I have the L score, The mean value refers to the average height of people. For example, if I am 150 centimeters and the average is 175 centimeters, then I take the square root of that to get the standard deviation. This represents a quantity I call the quantum model or statistical noise. The statistical noise that exists statistically increases as the value of the standard deviation rises, which means the amount of variation in people's heights increases, and the amount of noise increases as well. The same applies to images. Your image consists of pixels, and each pixel has a value. If there is a large variation between the pixels, not all pixels have the same value, then the statistical noise will be high for you. On the other hand, if the variation is very small between the pixels, then your standard deviation will be low. This is what we call statistical noise. But what is the signal-to-noise ratio? The signal-to-noise ratio is a type of, it's about the signal, which is perhaps yours, and what about the noise? When we recalculate, the standard deviation is the square root of n, which is the same as the square root of n. Okay, there is a point. Before I get into the topic of the equation, if I came today I injected the patient with a high dose with high activity. This high activity will give us high counts. For example, if I say I will collect 100 counts and then slightly increase your dose, you will collect more counts, say 1,000. If you slightly increase the dose you administered to the patient in this case, or increase the time of the examination, instead of collecting 100 counts, I will increase my time, so I will collect 1,000. Okay? For the counts, if you calculate the standard deviation for 100, you will find it to be 10. As for the standard deviation for 1,000, you will find it to be approximately 31. How? So, does that mean you want to tell me that the standard deviation tends to increase with the increase in the number of counts? So, this standard deviation can be considered as noise, in essence? Yes, it is. What we calculated is essentially a statistical value, which is called the absolute value related to the Gaussian distribution of your counts. But the real noise that you see on the image is what they call relative noise in this context. What is relative noise? It is 1 over the square root of n, which is related to what? If your number of counts is significantly high, then your relative noise will tend to decrease as a result. I apologize. It's not 1 over the square root of n. It is actually sigma over n, where sigma is the amount of statistical noise concerning your number of counts in this scenario. So, if the number of counts you have is normal, your relative noise will decrease. This means that when I talk to you and say noise, or in the question that comes, it refers to relative noise, unless they mention the term quantum model or quantum noise. This refers to the statistical noise, which is the standard deviation, but the noise or relative noise will decrease, which is the standard deviation relative to your number of counts. This is considered relative noise, which has an inverse relationship with the number of counts. If you increase the number of counts, your relative noise will decrease. If you increase the activity, you will consequently increase the number of counts, and thus your relative noise will decrease. If you increase the sensitivity of the gamma camera, you will also increase the number of counts per minute that you obtain per megabecquerel. Therefore, in this case, you will also reduce the relative noise because you have increased the number of counts or collective counts. We might have talked about this story before. In the previous lectures, you will find the difference between relative noise and statistical noise explained, along with the equation. If you look at the noise, you will find the difference between relative noise and statistical noise clarified. So, the noise here in nuclear imaging acquisition is related to the activity sensitivity of the gamma camera. But keep in mind, as we mentioned before, that with an increase in